So we want to solve this circuit by the method of series and parallel equivalent circuits. The circuit is a capacitor network where the capacitances are shown in microfarads. So first, let's identify the nodes of the circuit. And we do that by highlighting the maximum amount of contiguous wire as possible. So for example, in the upper right corner, that would be a node, and we'll call it node A. So let's give that a label. Now we'll continue, again, highlighting as much contiguous wire as possible. And so if you look at the bottom of the circuit, that would be the most I could highlight without going through a capacitor or branch. So let's call that node B. Also notice that node A is not filled in or shaded, it's unshaded. And I use unshaded nodes when I'm showing a node that joins together two branches only, two and only two. So the 100 microfarad and the capacitor and the 10-volt battery connect to node A, so that's two branches, so it's unshaded. Node B, on the other hand, I use a shaded node, or it's filled in, colored in. A shaded node joins together more than two branches. So node B joins together the 150 microfarad, the 350 microfarad, and the 10-volt battery. So it's a shaded node. And then we continue. So here is another node. Let's call it C. And last but not least, our last node, and let's call that D. Now, the technique I'd like to use is to redraw the circuit, and so I want to list my branches and keep track of the nodes that they connect to. So for example, the 100 microfarad capacitor is connected between nodes A and C, and you'll see the rest of the list. So the technique is to, which is good when you have a single battery, is to take the nodes that connect to the battery, in our case A and B, and force yourself to draw all the nodes along a diagram that's linear, straight line, where node A is on the left and node B is on the right, and the other nodes fit in between. So our battery is connected to nodes A and B. Now we just have to account for the other branches, the capacitors, correctly. So there's our 100 microfarad capacitor between node A and C. The 350 is from B to C. We have 150 between B and D, and the 75 between C and D. So the purpose of this is to more easily see the series and parallel combinations that are not so obvious sometimes in the original circuit, whereas here you can quickly see that the 75 and the 150 are in series, that result is in parallel with 350, and that result in series with 100. But since we're solving the network, which means finding the charge and volts for each capacitor, let's make a table and go through this step by step. So I'm making a table listing my capacitors. The headings of the table are charge, capacitance, and voltage. And since charge equals capacitance times voltage, we can basically organize our math in the table and not get lost in the details. So again, looking at the network drawn this way, we see the 75 and the 150 are in series. Now, capacitors are in series when they share one and only one unshaded node. So 75 and 150 share a single node D, and that's unshaded, so they're in series. So we can replace them by the equivalent amount, which is the inverse of the sum of the inverses. and that is 50, which then I also add to my table. Now you can also see the 50 is in parallel with the 350, because in parallel, the two capacitors must share the same two nodes, in this case, B and C. So capacitors in parallel, you simply add the values, so that gives us 400. And there's our 400, and I added it to the table. And notice now that node C is unshaded because it only joins together two capacitors. In fact, that then shows that the 100 and the 400 are in series. So the inverse of the sum of the inverses of the 100 and 400 gives us 80, and we added that to the table. And if we were simply looking for equivalent capacitance, we'd be done. But we want to backtrack from the 80 through our circuits that we produced, so that we can calculate the charge and voltage for each capacitor. So initially, we're given 10 volts on the 80, right? And so since the first column Q equals the product of the second two columns CV, that gives us 800 microcoulombs. Now, the 80 actually replaced the 100 and the 400 that were in series. And the key here is that in series, charge is the same. So the 800 microcoulombs that we found on the 80 microfarad equivalent capacitance, that 800 microcoulombs must also be the charge on the 100 and the 400. So we add that to the table. Now we have those two rows with two of the three quantities shown, so it's easy to calculate, in this case, volts. Charge divided by capacitance, Q over C, is volts. And so then we get 8 volts for the 800, for the 100 microfarad capacitor, and 2 volts for the 400 microfarad capacitor. And we continue. So that 400 microfarad capacitance had replaced the 50 and the 350 in parallel. And so since in parallel voltage is the same, we'll take the 2 volts that was on the 400 and say that that must also be the volts for the 350 and the 50. Again, we have 2 rows now with 2 out of 3 quantities shown. So we can calculate, in this case, charge. And again, charge is the product of capacitance and voltage, so we get our 700 microcoulombs for the 350 microfarad capacitor and 100 microcoulombs for the 50 microfarad capacitor. Last but not least, the 50 had actually replaced the original 75 and 150 that were in series. And again, in series, charge is the same, so the charge we calculated for the 50, the 100 microcoulombs, that must also be the charge for the 75 and the 150. Aha, now we have, again, 2 out of 3 quantities in those 2 rows. We can calculate the volts, V equals Q over C, and that gives us 2/3 of a volt for the 150 and 1 1/3 volts for the 75. And there you have it. We've calculated the charge and voltage for each capacitor. We've solved the circuit by the method of series and parallel equivalent circuits.